Thank you. Cool. It's good to be here. It's been, what, 4 years of building on top of AMD, and I'm going to share some of the lessons learned. So I'm going to tell you about ScalarLM, which is a new framework that's available today on TensorWave, which makes it really easy to get access to MI300. My favorite things, I'm just going to summarize the whole thing. My favorite thing so far of AMD, you guys listen to feedback. As a result of listening to feedback, you have the highest capacity accelerators in the world, and those allow us to train the biggest models in the world. And that's why, to me, as from an AI research perspective, AMD is very interesting. So, of course, having worked on CUDA long ago, the software stack is an important piece of the puzzle, and it's a lot. There's a lot in the software stack. So I'm going to share some lessons learned, and I'm going to introduce you to some pieces in ScalarLM. ScalarLM is open source, so if you want to go and play around with this or check this out, we have a preview release. It's a v0.5 release, fully open source. Feel free to take a look at this, and my hope is that we can, over the next, maybe 3 months, 6 months, we can really level up the ability to train very large-scale models and take advantage of the huge memory capacity on MI300 and beyond. So how do I press the, all right, let's, yes, wonderful. Perfect. Okay. So I'm going to start by telling a little bit about applications. Why did we do this? What are we seeing in AI applications that are leading us to create frameworks that are a little bit different? And then I'm going to tell you about the framework. Okay, so it's been almost 10 years since I've been looking at scaling laws, and scaling laws are still the most exciting thing to me in AI. Scaling laws are a recipe for intelligence. You can just keep making the model better and smarter, and they went from chat models to models that can write code to finally models that can reason, and there is no stopping this. This is just going to keep going. So, as you can see, I'm a little bitter about not being cited by OpenAI given we had the first paper, but I agree with OpenAI that this has been the driver of all of the progress in AI that we have seen in the last 5 years. And scaling laws keep scaling. It gets expensive, and this is why we care so much about compute, but they keep scaling and they're going to keep getting smarter. So as smart as the models are today, in 10 years from now, they're going to be super intelligent, and that's why we're calling them super intelligences. They're very impressive today. They're going to keep getting smarter. One thing that is, I'm sure everybody has seen this, is that the largest companies in the world are training on enormous systems of tens, hundreds, millions of hundreds of thousands to millions of GPUs to train the frontier models. It's extremely expensive. Why do we have to do this? This is from Ilya's keynote slide in NeurIPS. A number of AI researchers are asking the question today, why is this a limit? Why can't we learn faster? Why can't we scale faster than scaling laws? We're going to get there anyways, one way or another. We're going to get to much more intelligent, super intelligent models, but are there algorithms that can run even faster than this? And I think it's wonderful that he picked this slide, which is basically showing scaling laws in nature of the size of the brain as evolution created animals with larger and larger, with more neurons brains, except for people, which broke the curve and are much smarter. And I think it's funny that it leads to capacity. And that this is why I love AMD of taking feedback and building systems that have higher capacity. Okay, so what would that enable if we had super intelligent systems? This is an example of a web app, a map web app, about 2,000 lines of React code that Claude 3.5 came up with. So this is what models can do today. What do super intelligent models look like? What are they going to be able to do? They're going to be able to write system software and design chips. They're going to be able to design new drugs and discover new therapies. They're going to be able to build entire data pipelines from scratch. And they're going to be able to build our most complex and sophisticated applications that we depend on today, like autopilots or control systems for robotics. So these problems are going to fall over the next decade, and these are the ones we're really interested in. Chat is great, but these things are going to level up the economy in a way that is unprecedented. What do we know about these algorithms so far? So I want to share some of the things we've learned about these algorithms. I think DeepSeek is a perfect example of a step towards this. We're saying, chat's great, but goodbye chat. Chat is not good enough. We're introducing reasoning. You saw an example just now of reasoning. Reasoning, in my opinion, is a step towards super alignment or a step towards super intelligence. What does that look like from a framework perspective or a computational perspective? Well, we ask a question. The model thinks about it. It thinks through, it reasons through the answer. It does inference. It generates tokens. And then we use the result of that inference, the model's planning and thinking and reasoning through, to train the model using reinforcement learning. So we actually are starting to see the frontier models not just perform backpropagation, not just train on the common crawl dump of the internet, but think through and reason through all of that information while it's training. And so this is why we're building, we think there's a couple ingredients. You take frontier models, you take data, you take alignment goals. I'm not going to go too much into alignment, but then you produce these much, much smarter and faster models. This is kind of what I mean by super alignment. And this kind of leads us to why we need new frameworks. So ScalarLM is an attempt at a first framework that tries to add some of these new capabilities aimed at super alignment or super intelligence. And one of the first building blocks that we know that we need is we need both training and inference. So we're pulling open source code from Megatron Core, the distribution strategies from Megatron Core. We're running all the models in Hugging Face. We want to extend the abilities of models that are pre-trained. And we're adding high-performance inference engines like VLM. And we're putting it all together into a single software stack so that the model can learn while it's thinking about its data. So we think, I just want to show some things we can do so far. So that's what we're trying to do. Let me show you some things we can do so far. We can train 70 billion parameter models. This is running on a TensorWave MI300X node. We're using a small amount of memory, so we can actually push up. We're using 30% of the memory on 4 GPUs. We can push this up to about 400 or 500 billion parameter models. So we can actually train, not just run inference. Training takes more memory. We can run training today functionally on these systems using this framework. So we can run big models. This is just trying to understand the ecosystem a little bit better of where existing software stacks focus and where ScalarLM fits in. The main thing that we have is training and inference. You can do both training and inference without a separate framework. And we have mainline ROCm support. So our mainline containers that are regression tested are built on top of ROCm, and you don't have to go through a complex development process to run, to rebuild. You just use our mainline, and we test and validate on ROCm. There's other things I'll just point out a little bit. There's some, I'm not sure how useful this is, but I'm just curious from a developer perspective. We often do embeddings, and we often fine-tune our embeddings and then use the fine-tuned models. So we also have an inference and training engine for embeddings. Okay. One way to think about this, and this is looking at the software ecosystem, where does it fit in? We're one layer down from things like the Llama stack. So a framework that has training and inference, on top of that, you can build agents, you can build memory augmented systems like RAG, you can build inference, of course, you can build evals. We're also starting to see post-training, reasoning, synthetic data, reinforcement learning. And we see that there's convergence across the community of this layer of a framework emerging on top of the inference and training engines. Okay, and this is just a block diagram of some of the architecture design decisions that we put into ScalarLM. There's some things here that are probably a little controversial. In order to do inference, we're not talking about time to first token because we have to think about reasoning and we have to think about chains of agents. And so the way that we do queuing and scheduling of requests is different when we're thinking about long chains of agents that are talking to each other. So we actually have a different way of doing queuing in front of VLM. We're using the distribution strategies out of Megatron Core, but Megatron doesn't support Hugging Face. So we're supporting the model library on Hugging Face glued together with the Megatron distribution strategies. This doesn't even exist in the NVIDIA ecosystem, by the way. It is a huge pain to put both of these things together in any ecosystem, AMD or NVIDIA. And finally, we're pretty opinionated that in order to do distributed training well, you need to use MPI, you need to use Slurm. We also wrap the whole thing and run it on top of Kubernetes, so you can still deploy it in the same way that you deploy applications, but we're using the bulk synchronous SPIMD model that's kind of inherent to these frameworks that allow us to write fast, efficient implementations. And finally, we have a little glue that glues the models together, so the models that come out of the training framework immediately go into the inference framework, and there's no separate deployment process. They use the same shared representation of a model. Okay, so that's what we're building. If you have feedback, I would love it for people to give it a try. You can run it on TensorWave today. TensorWave we really like because it has a lot of access to MI300. It's available. It's easy to use. So if you want to download it, contribute it, share it, go check it out. Give us your feedback. This is V0.5. We're mostly testing functionality from a feature perspective. Let us know what else you want to see. I'd love to engage with the community more. If you're like a hacker, I would love to have hackers contributing to this if you're really good. And yeah, I think that's it. V1 1.0 is going to be perf. Thank you.